So I will first make a small, give small explanation of why the turbulence is important in accretion disks and what is the magnetorotational instability. Also on what is the shearing box supposed to mention, and then explain my setup and give my results. So if we want to do modeling of accretion disks, the quantity that is observable is of course the luminosity, which is related to the accretion rate, because the energy supply is energy of the gravitational orbits. But the accretion rate is of course limited by the angular momentum transport, because if we want to equate mass, we have to get rid of the angular momentum of this orbiting mass. The problem is that the microscopic viscosity in realistic astrophysical situation is very small and is not sufficient to provide high enough angular momentum transport. That's why we need some way to enhance the angular momentum transport, and that is the role of the turbulence. Usually this turbulence in accretion disk is parameterized as this alpha, Saniev and Shakura parameter, which is a way to non-dimensionalize the angular momentum transport. Concerning the origin of this turbulence, after looking for hydrodynamics instability, people of Balbus and Holle have found that accretion disks in general were unstable when a magnetic field was present. So just an explanation with the hands. What is this instability? It is due to the fact that magnetic force acts a little bit like springs. So if we take a Keplerian orbit in the disk and two elements that are on each side of this orbit, the one on the inside rotates slightly faster, so it will start to be in advance compared to the other one. But because of this spring, that is the effect of the magnetic field, this one will be slowed down and this one will be accelerated. So by this process, actually what happened is that there is angular momentum transferred from this element to the other one. So this one will fall on a smaller, lower orbit, while this one will go on a higher orbit, and then so on it will go. So this is the basic idea of this instability. As you see, what we only need is that the angular momentum, the angular velocity decrease outward, and in ideal MHD this work with even as small as you want for the strength of the field. It's not true with non-ideal MHD. So to study the turbulence that is created by this instability, the usual thing is to study it in a local approximation. So we take a box that is rotating with the disk at the Keplerian orbit. So in this box is a rotating frame, and the differential rotation that was present in the disk become a shear, which is linearized in the local approximation. So what was the r direction become x, what was the y become, what was phi become y, and z remains z. And how this shear is implemented, there's two things actually. We use shear periodic boundaries, which means that in usual periodic boundaries, one point on these boundaries correspond to the opposite point on the other boundary. In shear periodic, the correspondence is the same, but shift with time along the other boundary with the shear velocity. And so all the variables are shear periodic in this sense, but we don't forget in the equation that it is this variable that is periodic, and the true velocity also contains a shear term, which is just a linearization of this one. And this box, the MRI is also present in this kind of system. So, what are the purposes of my simulations? It would be interesting to have mean field models for this local situation. We would like to have predictive power of this mean field model. For this, I use the mean field dynamo formalism. Even if it's not a real dynamo, because in my case I will use an imposed field. So the point is to relate this quantity to the mean field, to have a real mean field model. To do this, we need to measure these two tensors. The average that I will use is average along horizontal planes. So the usual ansatz for the EMF can be written in this form. And this is the first step. Of course, the second step would be to find the relation between this tensor and B to have a real predictive power. But first, we need to find that. And then concerning the boundary condition at the top and the bottom, usually what was used was also periodic for the top and bottom boundaries, but it was found that in this case there was a convergence problem, which was that the turbulence level varied as some power of the magnetic Prandtl number, which means that when we decrease the Prandtl number, the turbulence becomes very weak, and also the angular momentum transport. This is for non-stratified and fully periodic box. It was found both in the case of zero net flux, which means without magnetic net flux across horizontal surfaces, but also with vertical imposed field, which is what I am using. But recently, Petri has shown that this problem actually disappears when we use vertical field boundary conditions on the top and the bottom. This was done for zero net flux, so it was first reason to use vertical field boundary conditions was to check if this convergent problem also disappears with vertical imposed field and not zero net flux. Another reason was that first I was doing stratified runs, and with stratified runs we cannot use periodic boundary condition at the top and the bottom because of the stratification. So usually what is used is vertical field boundary conditions. But while I was doing that, I realized that what I saw seemed to be mainly due to the boundary condition. So I wanted first to check what is the effect without stratification of these boundary conditions. So the numerical setup, I have already explained the box. I use mainly 64 cubed resolution. This is the strength of my imposed field. So we have rotation, imposed field, and shear. I use PM between 2.5 and 4. Magnetic Reynolds number quite low because of the resolution. This is the Reynolds number of the box calculated with the scale of the box and the rotation. It's not the one calculated with the RMS value. And I remain weakly compressible because my Mach number remains small. So as I said, I will be using horizontal average because my situation is completely homogeneous in the X and Y directions. The only direction which could be inhomogeneous is the Z direction because of the boundaries. So I expect only variation in the Z direction. So here is what I get after. So there is first the linear instability, so an exponential growth, and then a saturation which reaches some kind of steady state. But what we see, these are the RMS value of velocity and magnetic field. what we see with the magnetic field is that there is a quite long transition period, and if we look at the mean field during this period, what we see is that actually there is two different phases with two different mean field structures. So this is the y component of the mean field, depending on the height. The color shows the strength, and we see the evolution in time. So this transition, this period actually corresponds to a phase when the mean field has a anti-symmetric profile in the box, and then it becomes more symmetric. If we look more in detail at the profile, here we see the profile averaged over these two phases. So what we see, as I said, in this case it's anti-symmetric, in this case it becomes symmetric. The transition is quite sharp actually. And the other point is that there is really strong gradient near the boundary, so I will come back to that later. But the fact that this is only a few grid points, so I was thinking that it could be a numerical effect. But first, another time series. This one shows a comparison between the magnetic energy that is in the mean field compared to the magnetic energy that is in the fluctuating field. And what we see is that actually after the transition, the fluctuating field becomes really weaker than in the first stage. So the turbulence in some sense decreases between the two phases. So this transition is quite puzzling. I haven't yet found what is the mechanism that switch from one to another. But to come back to what I said, but is there resolution dependence? So I did a direct comparison between the same run but with two different resolutions. I superposed the profile, and it seems that there is really no dependence on resolution. So it's really a physical effect of the boundary conditions.
But
yes?
is it on the same number of grid points or on the same physical length?
No, it gives the same physical length. So then, to speak about this convergence problem, so I did a few runs with different magnetic quantum numbers to see if there is a dependence. As you can see in the level of the turbulence, there seems to be no strong dependence. Here is quite a small range of variation. This run is not really reliable. It crashed before reaching a steady state. So
you could also do 0.2 maybe, right? And maybe even 0.1 for the Prandtl number.
I'm not sure that I can with my resolution. It would crash.
Then yeah, maybe you need more resolution simply.
Yes. And this is the same for this alpha Sonia-Fan checker parameter. Here also we see that there is no strong dependence. I've used this definition, which is not really the one that is used usually, but it was the one that Petri used in his paper, so I wanted to compare the values. And what is a little bit weird is that I found something around 0.03 and he found something around 0.3. So I'm one order of magnitude smaller, but we would expect that with an imposed field I should have a bigger value. So maybe it's a problem of this definition and of the fact that in Petri's run he used higher sound speed than me. It should maybe be an issue.
Were these data derived from the final state?
Yes.
Where the field is symmetric?
Yeah, everything here is average only on the final stage. Because the previous stage has two big fluctuations and I can't do good averages. So it seems that there is also no dependence on the magnetic quantum number in this case. So vertical field really, vertical field boundary conditions really allow to get rid of this problem even with an imposed field. And then, so I did a measurement of the alpha and eta tensor. As a first approximation, I neglect non-local effect, so I use only linear test fields to measure alpha and eta as functions of the height. So here are the different components, it's not really visible. This is alpha xx, yy, xy, and yx. The important point here is that this component is very small compared to all the others. It's 10 to the minus 4. And this would be the one that would create bx field from the by field, which is what we need because we have shear to create back the by field. I did the same for the eta tensor. Here there is two remarkable points. First, that these two components, eta xx and eta yy, don't have the same shape at all. It's not really a surprise because my box is not isotropic. Y is the direction of the shear velocity. But here we have also a strange thing that this part is negative and very strong. It's even stronger than the microscopic diffusivity, which means that there is a negative total diffusivity near the boundary. It would be maybe a strange form. The other point is that this component is 0, which could also create bx field. So I have no components that could create bx field. I have tried to reconstruct the EMF to see if this measurement gives something, at least some explanation of what I have. So if we take the induction equation and average it over the final steady state, this should be 0, so all the terms should balance each other. It's true if I take the measured value of each term, but if for this term I try to reconstruct it from the alpha and eta tensor, it doesn't work. And more precisely, if I compare the measured value of this rotational of the EMF with the reconstructed one, what I find is that there is a difference of 1 order of magnitude. So reconstructed value is 1 order of magnitude too big. And the other interesting point is that the effect of all the components of the alpha tensor are always negligible compared to the effect of the eta tensor. And for the x component of this, it's the turbulent diffusion that dominates, and for the y component is this eta xy that was quite strong, which dominates. Here what I have plotted are the x and y component of this. The solid line is the measured value, but it has been multiplied by 10 in order to be visible, and the dashed line is actually just the dominating component of both reconstructed values. So we see that it's really not in agreement. There is two possible explanations for this. The first one was that that for this we haven't taken into account the alpha xz and yz component, which represents the dependency of the EMF on my vertical imposed field. I have now started to measure also those components, but it seems that it's not sufficient to give an explanation of this problem. The other explanation would be that I have to take into account non-local effect and so to measure alpha and eta depending on the wave number of the test field and with a Fourier decomposition.
But how strong is the influence of including the alpha I3 components? So it changes something, but not enough. But
Yeah, not enough. It's on the same order than the other alpha components.
So it's more or less negligible.
Yes, usually it's the order of the microscopic viscosity and things.
So it would not change this picture at all.
No,
Not visibly.
maybe the shape of this, but not the order of magnitude.
But in any case, it's really small length scales of the mean field, of course, that are being
Maybe.
this of the EMF,
Yeah.
but not being
But this
reproduced.
is a non-local effect should be.
Should be important.
Yeah.
I think so. Yeah.
Yes.
But that is true everywhere or just on the edge of your computational box?
Actually, the point is that, as you can see here, everything happened near the boundaries, on the bottom and the top.
But in the center, the two are essentially the same? Or is order of magnitude different?
No, the point is that this rotational here includes. Yeah, no, it's very small here because there is no gradient of the mean field. All the variation of the mean field occur here. So that's why everything. Actually, my field is almost uniform in the box, and there is just something happening near the boundary. So it's really an effect of the boundary conditions. And the last thing that I found a few days ago, and that is a little bit surprising, I tried doing a 2D run of the same thing, and I also found exactly the same transition with the same repartition of magnetic energy between the mean field and the fluctuating field. And after doing that, I looked at my 3D run, and actually, after this transition, the Y dependence almost completely disappeared. So the 3D run becomes almost two-dimensional after this transition. But here, it's in the first phase, the 3D run is really three-dimensional. So it may be that the Y extent of my box is too small, or that my magnetic Prandtl number are too small also. So I'm planning now to.
So in the 3D run, in the very first stage where you have the linear stage of the MRI, you really see a specific wave number in Y?
No, in the in the linear stage, there is no.
There's no relevant Y dependence.
No, it appears only just after the end of the linear phase.
So we may conclude that the MRI
Yes.
is fastest growing even for the wave number in Y direction 0.
Yes, that's true. From the linear analysis, is that the result is that
That's confirmed.
kx and ky equals 0 is fastest growing one. And you can see it here because you see that the first to grow is the mean field, and then there is something growing in the fluctuating field, and modes with kx or ky different of 0 would appear in this part of the field. So we really see that it's first kx and ky equals 0. And so here's the summary of my results. So first, that there is no more convergence problem when we use vertical field boundary conditions, even with vertical impulse field. Then the second point is that vertical field boundary conditions seem to have a strong influence on the turbulence and on the mean field in my box, because we find this transition of the mean field structure that wasn't apparent with periodic boundary condition. We have also seen that the EMF is concentrated, the effect of the EMF is concentrated near the boundaries, so everything happens in thin layer near the boundaries. And then that's the alpha tensor and eta tensor that I have measured failed to provide a reconstruction of the EMF. As I said, there is just two possibilities. This one seems to be not sufficient, but then it will be this. And last point, this thing with the Y dependence that disappear. The point is that in the shearing box, the shear tend to stretch the structure in the Y direction. So effectively if my box is too small in the Y direction, the stretched structure will become Y independent because of the periodic point of recognition in this direction. So that's why now I am trying to do a run with a bigger box.
Thank you very much. Questions, please. Yeah,
You say that the alpha and eta tensors don't allow the reconstruction of the EMF. And you mentioned two possibilities, but there's another one. You have only considered the alpha and the eta tensor. That means alpha goes with a B without derivatives. Eta tensor goes with a current, electric current. But in general, you have also other terms at this place which cannot be described by the current. In general, you have to write a tensor of rank 3 times gradient tensor of B. And we just learned from other considerations that these parts which are connected with the symmetric part of the gradient tensor of B, not the current, but the symmetric part, can be, the coefficients can be larger than the coefficients which you have in eta, which describes the influence of the current. Maybe this is another possibility.
But I mean, he has defined horizontally average fields, so then there is no other possibility. There's no other gradient component in the horizontal direction.
Averages, there's no such term.
Yeah. It means, mean fields depend only on one Cartesian coordinate. So then I shouldn't say this.
You showed this plot with the exponentially growing BRMS.
Yes.
Is it growing fast enough that you can say that you have a dynamo?
It's not a dynamo because I have a vertical imposed field, so it's not really. But we can have the same thing with using an initial field that has a zero net flux, as Petri did, and then there is a dynamo. But for this we need higher magnetic resonance number.
Can you show the plot again with the growth?
Yes, what I think it will be.
You had a blue curve, I think, in a
with the blue and
yes.
green fields.
Right. It would be good to see that in logarithmic, because
Yes.
then you went to argue that this one actually had a faster growth, that you could only
Not
see
faster, but
saturated,
sooner.
yeah.
So it's maybe that this is appear only after non-linear effects start to be important.
Yeah. But I mean, I think it was a discussion that we had that maybe the m equals 0 mode really has a larger growth rate, which I find surprising because it's not the first mode that you see in the butterfly diagram. Right.
Which mode? The m equals?
M equals 0 or k, not n, but k.
Okay, well.
I mean, your lowest mode is neither of those, of course. It's actually maybe something like a half mode. You can also call it a quarter mode.
In the y or x direction.
Yes, it's a one, of course, the basic mode, right, which has two nodes. I mean, two half nodes
Yes.
in the top and bottom.
But in
Z.
the
In Z.
with the local linear analysis, we find that the fastest growing mode is really kx equals 0 and ky equals 0.
Kx equals ky. Aha, so axis meter, yes.
But there are several modes
Right.
with different
Yes,
KZs,
yes.
of course.
Yes.
With
And
different growth rates.
yes.
But it's a real interesting question. Why in the saturated state, all of a sudden there are modes or constituents that depend on y, or context, whereas they are not there in the linear state of the MRI. So what is the origin? There are two possibilities, I think. There's another instability we have not thought about yet, or there's this effect that which was observed in maybe first, or which was observed in the dynamo context, that the mode which has the largest growth rate in the linear state is not necessarily the one which shows up as the dominating one in the non-linear state. But this requires, I think, that the growth rates of, in this case, say kx equal ky equal 0 and kx or ky unequal to 0 are more or less similar, close by. If they are not close by, well, I cannot imagine that all of a sudden a non-axisymmetric mode would dominate here. So this needs to be explored. What is the reason for this switch from axisymmetry, say, to non-axisymmetry in the situation state?
And then back again, of course.
And later on back, but this is even another story, I think. Because we have, for the first switch from a linear state to a saturated state,
Okay,
we have
yes.
to
Yes.
think that this is saturation of the MRI.
Right, yeah. No, I agree, yes, absolutely.
I think that I've read something about this, that the mode of the first growth become unstable or something.
Because the background field has changed in some sense.
Yes.
Oh, yeah, that might be.
Yeah, but the... Yeah, I'm not quite sure. I mean, the axisymmetric, the completely only z-dependent mode, the one-dimensional mode, that one we know cannot actually be saturated by the Lorentz force. So it's bound to be an unphysical one, if you just allow for that, because that one cannot saturate.
So the field grows and makes another mode unstable.
Yeah, and it's only one of these other ones, of course, which has the ability to saturate the solution. The solution has to be saturated, of course, otherwise it would be continuous energy conversion, 100%. Yes, I think that's actually weird. What is actually wrong with that? Suppose we had a one-dimensional MRI, then the energy goes all the way to it. I mean, it grows exponentially, of course, for all times.
Well, your ideal physical system does change after.
Yeah, but I mean, the Friedmann box has, of course, the ability to tap energy at an
infinite rate.
not
Enclosed here allows you to do input energy at an arbitrary rate.
yes. Which is of course exactly, it's not arbitrary, of course, it's a fraction of omega, as you know.
And you might be able to do arbitrary. Well, okay.
No, it depends. It depends on the shear. It depends on the order constant. That's what taps the energy, and that will actually grow exponentially.
But that is only in ideal energy, right?
Yes, but for large RMs, it's still true.
Slightly modified the curve.
Yes. Yes, you have done some experiments with embedding. I mean, the vertical field condition is in unsatisfactory situation, of course.
Yes.
One should be careful with that. But one method out of that is to use an embedded.
Yes, I
Halo,
have
which I've
finally
tried, right?
obtained a saturated bron. It seems to be really different from this situation. The structure of the main field,
But with what?
using halo with high diffusivities to change the Bron recognition.
So what's different with the other?
I'm not sure because actually it's also crashed, but sometimes after the saturation. So I had some time to see, and it seems that there is more like k equal 1/2 mode in the box, something like that. But I'm not sure, and because near the boundary, near the transition between halo waves.
So Have you tried to measure the alpha Shapura-Smith as a function of height?
No, but I think actually it would be higher in the boundary layers.
Yeah, because I was wondering
Yes.
how much of that number that you get
Yeah, I
comes
think it
from
would
the
be.
bulk of the
No,
flow
I
versus
haven't
the
measured it, but
edge.
So you remember, he has no stratification, so the density is constant again.
Yes, but
but
Then it's simply strongest where the field is strongest normally.
what are the differences?
No, the alpha is magnetic.
Yeah.
Yeah, but it does depend on the product, BX, BY, of course.
yes, and in
Angle.
the bulk of the box, px is almost zero, so I think it would be mainly in the boundary layers. They haven't measured it.
Mhm.
This could be different with the halos.
Yeah.
Yes, it could be different as
Are
well.
you generating flows at the top? Like,
Yes.
there
There is flows near the boundaries also, and there can at least one component can be explained uniquely by the effect of the mean field, the mean Lorentz. The Lorentz force due to the mean field can predict the flows.
You have accretion of the
There is yes two in opposite direction on the top and the bottom.
Oh, you mean in Y or in X?
In x and y dimension,
Yeah.
but it's
So this balance
in
will
Z.
Yeah?
In Z.
Not in Z,
It's
it's,
not
it's
at the
close,
top
of
and
course.
bottom, there's at the top and bottom of your box, there are two separate x-directed flows that are counterpropagate.
yes.
But why?
There's no.
But there are also
direction.
propagating in the y.
Also propagating.
Going flying.
Yes.
Yes, I think the X one is the primary thing.
Yes. The
So it's
X one
something like
is
it's like a channel solution. One of these channel solutions. They go like this, of course. They counter streams, and if you
Why are they not accreting both of them?
hmm?
There is no accretion direction.
There's of course no yeah.
Yes, this box is symmetric for x direction. There is no inward and outward.
That's where the energy is coming from post shear, like the natural accretion plot.
No, you have but you still have a Fourier force.
Yes.
So that tells you there is a direction.
That tells the direction of the angular momentum flux, but not of the mass flux. You cannot.
There's no mass flux.
So, but if you have the box here, right? So here's the central object. You put your box here. Then of course there's a direction, right? Which is inward. Okay. This is out. Angular velocity goes like this. Locally in the box. The box is moving with the flow. It's moving with the flow. So it's in the box. The shear flows like this. Everything is okay, right? Now you have the orbit. And the box here. Again, these parts are moving more slowly. These are moving faster. The whole box is moving. Angular velocity is still in the same direction. Now where's in and where's out? In is of course here, right? But what's the difference between these two boxes? Forget about all of this here. What's the difference? Where's the difference?
The downwards motion has been transformed out of the box. The box doesn't know it's moving.
Yeah, okay, but there is a difference in the angular velocity with respect to the two velocities.
Yeah, the point is the box doesn't know its velocities.
So the point is that you want to have accretion, you will have go beyond linearization. Right?
Yes.
And it's have a
You have
curvature.
to have a second derivative.
Yes.
So in order to, so in other words, if you have a derivative like this, for example, then it may need to be transformed into one with a d by dx, and then with a minus 1 over capital R, a plus. And whether or not you have a plus or minus tells you whether the radius is in or out.
So do you know if anybody has ever done non-linear association blocks?
You mean this one?
Yeah.
Yes, this one we have done in 96 already.
And then you can see when after.
Yes, of course. Then you, by the way, you get an m dot. Only then you get an m dot, right? And you know, of course, what m dot is, it's supposed to be equal to 3 pi times nu turbulent times the integrated mass density, which is this one. And that worked out, it's the case. Now there's another formula in that case.
This can also give you an independent values of alpha, right?
Yes, yes. So from this you get an alpha. Sorry, this was a sigma here. From this you get an alpha because you know you get ut. Then you have the heating rate. What's the heating rate? The heating rate is given by ut times also sigma times an omega squared times a 9/4. Again you get an alpha. And you can measure the stress as measured mxy minus rxy, something like this, maybe here. Like this. And again you get an alpha directly. You can compare these three. And they are all good. That was in the 96 category.
But how much more computationally expensive is
No, not more expensive. They're cheap. But it's still cheap in some sense. It's still not.
Isn't that a better way of measuring what we really need for alpha?
Because your boundary conditions, like before you have legitimate, one case you have sort of legitimate shearing periodic boundaries, and the other you don't no longer have legitimately shearing periodic boundaries. It's very much like that solution. So
I guess.
But at least we get out of your simulation what you really want.
well,
M dot.
you get m dot for a system with very specific power law dependence and things like height and stuff.
Any other questions?
Just this, did you do MRIs before you came here, or did you
No.
just learn
No,
all the things?
I haven't
just
done
in this
MRI before.
conference? How much work has there really been in doing this for with reasonable stratification for class?
You've done it, right?
Yes, but I have only tried this constant gravity field. As soon as I saw this thing occurring in the boundaries, I switched back to non-stratified to see what was really the effect of boundary conditions.
The advantage.
That stratification is very, very scary. The stratification is actually very strong and decreasing risks. So the effect of stratification is huge. So,
Yeah, but
everything that's going on the boundary is scary.
yeah. So were you saying?
And then to be
You were
close-
saying that stratification is very strong.
Yeah.
So does that mean one shouldn't neglect
Well,
it?
it means the fact that everything's are occurring at the boundary
Yeah.
is scary. That's all. That's all.
Actually, what I got when I was using stratification was instead of having the profile of my mean field, here I have something like that, and instead I have something like this. So the stratification was apparent, but there were the same gradients, and for the big files fields there was also this peak like this. So that's why I switched back to non-stratified
Have you
case.
tried? So you have not tried having an actual look.
No, it was constant gravity, so it was just a very local approximation out of the midplane.
I mean, the midplane would remove one of the boundaries, one of the other one.
So how much is what's the result of the electric field on your upper and lower boundary?
See electric field?
Electric field?
Yes.
I haven't measured it.
He is normally never used in MSG.
It's B plus B. What is it?
It's yeah.
Yeah.
Oh, I think it's maybe zero. Is it zero?
It's always zero.
What is the horizontal? I mean, the vertical component, you mean? Depends whether they I think it's the what conditions. So it's say ux. Let's even forget about this one, or maybe let's keep it. And this one is 0.
The boundary is
Okay, so yes. So then you have, then of course it's not always 0. And then you have, but for your vertical, no, this for the vertical field condition, this is 0.
yes, and there is only a busy.
So yeah, and then it's 0. Then, but of course the other ones also 0. No, the other ones are not 0. So this becomes plus the uy times z minus x.
This would be, at least in my case, would be quite small because the field is small compared to the other component.
There's a contribution all the time.
Yes.
This is only ideal.
Yes.
That one is probably actually also easy conversion.
In the z direction, it would be 0.
Anything else to improve from that? Why did you ask about equal speed? Yeah, equal speed?
No, I asked this because of the things that happen because of the boundary condition. And where you have a By that is basically a certain values throughout the entire box, but at the boundary you sharply change something, right?
Yeah, but the boundary condition imposes that it is 0 at the boundary. It's the 0 value here and here imposed by the boundary conditions.
But why?
It's a vertical field, so only the BC component is non-zero.
Can you sketch the field with the halo?
What?
Can you do that sketch with the halo? Yeah.
Yes, that's what I said before. But I did.
Could you simply sketch it in the same picture? What
Yeah,
would be
okay.
different near the boundary
Uh,
if we had the halo?
I'm not completely sure because it was very fluctuating. But it was
As
more
far as you know,
something like shape like this.
no sharp gradient.
No sharp gradient, but it was fluctuating and moving in the box.
But remember, the By field in the fairly first part of the saturation phase
Yes,
was antisymmetric
yes, it was a shape like this.
with respect to the middle of the box. Yes. And here too, you said?
No, there is no such phase in the
It was
with
symmetric.
halos.
Yeah,
With halo, it seems, but as I said, there is strong fluctuations, so I can't read it.
It's still in the second stage.
It
Not
seems,
the
it looks like it's a second stage. It's really fluctuating.
But we might get so that the boundary conditions have a strong influence.
Yes.
It's not inconceivable.
Yes.
It's a pity that it doesn't work well with the head.
Yes, and I don't understand because the last run, which reached saturation and crashed only after, the crash was not, usually it's just a time step that becomes too small. But there I found some infinite value in some variable. It was in the advective something, I don't remember exactly what it was. Something called advective or something like this.
And you have observed some peaks in the velocity.
This was, yes, before, but it's maybe because I was using a very sharp transition between the halo and the bulk of the box. And then I had some peak at the transition between the halo in the kinetic helicity and also in the UZ velocity. It's a little bit weird because my variation is only for the magnetic field, it's only the magnetic diffusivity that varies between A1 inside the
But if you have only a factor 10, then this sharp X disappears.
No, it was also
It was
there,
still
even with only a factor of 10.
So the diffusivity. So
You have also stress-free. You have a tri-stress-free condition at the upper and lower boundary.
Magnetic stress-free?
Yes.
Yeah, but that's what it is, by the way. Because stress-free means Bx and By equals 0. Just a fancier word. Same thing. Right? I mean, you want stress-free sounds so cool, always. You mean, of course, this should be 0. But that's just the same as the x times By, so how do you make that 0?
it's sufficient to have only one zero.
Yeah, only one.
Yes, you can make the x 0, but let By be free.
But then you need a second condition. You need two conditions in the magnetic field.
By is what it wants to do.
That is not a condition. You need boundary conditions to make it. But what is the boundary condition? If By is free, it's not a
But
condition.
it's true that BZ has a
It's
fixed
By in the Gauss zone is like By in the first.
Yeah, but
Zero order extrapolation.
Yeah, but not disregarding numerics, how you will be formulated mathematically. You need to have two restrictions
My
for the magnetic field.
My point is this: okay, you have, if that condition is true, there is a huge current. There is a huge current sheet at the edge of that box. So what you want to do, you want the systems where there are no current sheets. And so what you don't fix B to be 0, but you let it do whatever it wants, such that there is no current sheet.
Okay, then
at
this
the edge.
is the condition. Then let's say how to formulate that locally. That the sheet is not there. Current, yeah.
Yes, current is equal to 0.
But isn't that artificial again?
No, it's a reasonable approximation because
It's maybe more reasonable than that one.
because I mean, if you have a current sheet, it will be highly dissipated in any case. So that's why the A graphs are a better solution because they do exactly that.
Show maybe what's the plot that you had
What?
Show maybe again the plot. So you're saying Bx is 0?
On the boundary, yes.
Maybe By comma Z is 0, yeah? What?
No, the vertical field is Bx equals 0 and By equals 0.
Yeah, but what could be
That doesn't
done
work.
instead would be something like that. It would mean JX. It could be, and but this
Because
only because
Bx and By are 0.
I mean, it's yes. So this is maybe not as scary as this one, perhaps, because this one really got up and down.
but then the other way around. By equals 0 and JX comma Z.
But that also means you have a huge current laid on the Ly. That's my point.
In both. But if you drop one
In
condition,
both.
you will probably still have the who knows.
I'm not convinced actually because it's a problem with the magnetic field is that you change one condition in one and then you get current in the other.
We don't know.
And it sounds like you're arguing for a perfect conductor kind of condition in X and Y.
Which is not really so interesting anymore, because then, of course, we can't have it mean flux.
Well, you have perfect conductor on X and Y. You have a conductor equivalent equation on X and Y, and then allow for this is sort of like Bx comma Z is 0, By comma Z is 0, and there's zero derivative on fields.
Does that jump or sparkle change with the magnetic Reynolds number?
You mean
The amplitude.
the amplitude doesn't seem to change much. Oh, with the magnetic Reynolds number?
Yes.
I've only like 3 values, which were 50, 100, and 150. So it's not in big range of.
So probably the I mean, it could well be then. I mean, first of all, I think it's interesting that we have the more insight for this boundary condition. But of course, one of the things we might potentially learn from that is really that this boundary condition is a really bad one, which we didn't really know so well before. I mean, it seemed like the best alternative to a closed boundary condition, which is really also not good. And that this one is such a bad thing, if it is really bad, I don't think anybody knew. I mean, otherwise, perhaps we would not have done this paper.
And by the way, page 3 also from this transition in its ones.
So I would be, you haven't had time to really look at why the halos crack. That strikes me as just the next order of improvement.
I agree.
Yes.
I remember I ran actually such a thing, but then I had a toroidal field. That didn't crash. I think I even had stratification, but another interesting question is perhaps about learning the code, because you were asking whether you knew about pencil code. Sorry, about MRI. You didn't even know about Unix, right?
Yes.
As I think none of you either. But maybe about the code, because one of the things that will be discussed at the next pencil code user meeting is to say that there are some people who have made the comment that there are so many routines in the code that it would be much better to strip down everything from the code, so that you just have the bare minimum, and everybody is supposed to do the initial conditions themselves. Just because that would scare people away, and that would scare people less away. So in other words, you take the code, and of course nothing is working yet. You have to do everything yourself, and that would be less scary. Is the idea? Is that true? I'm maybe expressing it too strongly.
Something that might be interesting. This would be, I don't know how really how to this would be. It would be like a GUI equivalent to the current make command. So it's like you open up the magnetics thing, and you do trees like, or a it's like which forces do you want? Checkbox, 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 and so on. And then you hit the file.
But suppose for example you sit in New York and you open this GUI on Further, for example. And after it takes maybe 50 minutes to open this GUI.
I'm not saying this would be great. It might be nice to have available in some fashion.
Of course, it will be local.
The GUI which can also be non-GUI like.
The GUI must be local.
Yeah,
I
you
mean,
can
raise a file, the
use
file
it
is-
locally. And
I mean, if you strip down to ideal MHD, how many lines of code you end up? If you get a very stripped down version to ideal MHD.
I mean, I remember Rocky had runs the code, but it was as short as 8 lines because of the integrations.
No, but that could be a point, because if you have a core code which is short enough that a student can print and read pieces,
Yeah, that's probably true.
then it's also easier for him to learn and then plug more things.
But the problem is that already single subroutines are that long that you cannot read them.
Yeah, but that's exactly the point, that should be short. I mean, the core, the advanced routine for the many fields.
Yeah.
I mean, at the moment there is all kinds of mean field aspects in MHD, as before. I agree with that. It's really out of place in some sense. But then how do you... And then it's a lot of work, of course, to put it into some other place, but I mean, that's really what one should do. But that would mean we would have even more routines than before.
Good style.
It's a good style, yes.
Many routines with 100 lines.
And not only even more now. Yeah, but I think they actually meant modules. Any comments? Yeah, so was that actually a problem? Were you scared by the code?
it's a little bit big. It's not really easy to find what we're searching.
So what would you suggest what to do?
I don't know, maybe more separated module for very specific things. But I don't.
I think that what I'm one approach is one take an example that one kind of want to do like that example, and then one modify that example and kind of add something or subtract something. And that's a approach that I think a lot of people are using, that they take a sample and then they add the extra features that they want to use for. And that is
Right.
how to get into
But
the
is that, we have these samples.
Yes.
And you can start from one of them.
Yes, and I think that is the way that most people get to use the code to take something that works and build from that instead of building from scratch, because no one else can build from scratch.
Yeah, to use the code is not very hard, but when you want to read in the code what's really happening, it's harder to find a good place where the thing you should look for is.
So that means we should not at least strip away stuff just like that. Right.
But what Alex said, I like it. It's just to have this simple pattern to select things you want to have.
Or at least just make it so that instead of what we have right now, all the right-hand side calculation ones are every single place. Those are all each of the module. The place where I can't remember what the 17 names are. The one we picked at the right-hand side just have it do it's just a sequence of calls to functions. Those are all in their own separate file, and they're typically commented out, and then you just comment any ones you want. And then you can look for this later, or ideally have some sort of GUI set where you just do it and it runs everything automatically. Ideally, like get rid of one of the ifs and just have comment outs, and then
Ifs and the ifs.
like, so there's a huge amount of switches. Like get rid of switches and put them in make comments, and then have a GUI which generates a script which does the appropriate one comment.
I mean, by the way, that has also been discussed. We had in the past, we had a code which worked with compiler, what do you call it?
Directives.
Not directives. Are they called compiler directives? So it's a precursor. You run this code through a precursor. And so we had a code which was running in both Cartesian and Circuit. But it was so difficult to read. So in a sense you could say it was great because now it's so great. But it was impossible to read, even for me. But everything was, you no longer had a clear if and not if and stuff. Because everything was somehow possible. And then there was some unusual, there was not even color coding. So I think these preprocessor things are really not good. It sounds good if you haven't done it yet, but once you actually do it, it really would be nice. But the GUI, you mean, should actually transform the entire code? That's what you're saying, right?
You wouldn't necessarily transform the entire code, but maybe it would generate your run files, your cprams, and make file.local, start.in. You would write your start.in, run.in, print.in, xyaver.in, make file.local, and cpram.local for you.
But not any Fortran files, what you might have.
And it could potentially go through and do some Fortran stuff if people are doing that appropriate, but that's less important than having it just go through it and
I'm not sure people will be less scared if they see that they have a code. In the end, of course, the actual code that is really running just to make it less scary. So you have a very simple code. And then your preprocessor comes along and makes a special code.
No, that's not.
But this is
that's
the
not
point
fun.
actually the base step would be less a preprocessor than a automatic local file generator. So basically, it's rather than having a bunch of different local files, you have a GUI with options which can automatically generate local files for you.
We just did with it.
Which is just smart. You just like
But they're also already so. I mean, they can be as short as just maybe a few lines. You can.
But it's like it's 18 bazillion different files to look through, and you have to remember to actually check them appropriately, rather than sort of like having a nice checklist.
Yeah, but take an example. I mean, you have either entropy on or off. That's most common. It's quite straight off. Density is most commonly on. So why do it's by default is on? So many of these you can actually remove already. Then you have just your thing with just 2 lines maybe. And then you can say this. Whereas if you have a GUI, then you have, I'm not sure you just have two options. I mean, of course, a GUI would hide the fact that it is easy. The current thing would hide the fact that there's a lot of default settings. But if, I mean, if it's a GUI, so you have you really have all these choices, of course. Each time we have to
Check, but they're just there in a combined form.
And you don't need to look up how certain quantity is called. Because you always have
The names of the parameters. This is much easier if the GUI shows them something in the menu.
And probably you don't need to use the GUI if you don't know what to do. When you learn, you could use a sample or write it yourself.
I mean, the GUI should be only a tool for modifying the file. You can always modify it yourself.
Okay. Good. So then I think
And
we are
something
done.
else, we never get any of this freaking like order of start time in things.
Nice.
Yeah.
But for that, but wait, you know that there's a way to find that out.
You run it and it fails, and you look at it and you try it. You try it again.
No, what I mean, you get an empty name list. Too bad for you.
Yes, you get a name list. You try it, it fails, you get a name list, and then you go ahead
And you cut it and paste it in, and then it's ready. And that's already. What's so funny about this? Do you know any other code which does it and can do it?
Of the output file?
the name list for the one that in program.
I mean, the code, there's an error, and the code immediately tells you how to do it right.
Yeah,
But it's,
So I think that
Still
sometimes fails, because for me it sometimes fails.
actually, I know especially with particles, it gives the wrong question. And maybe there's some like design for it to be some sort of modular thing where all the different particles have the same one. But that's not sure what's happening. So if you have particles of dust as your particle module, then it actually gives you
does it exist as an?
I haven't tried the part with the particles name.
Yeah, but it has to do with writing a bug report simply. If it's not a bug report, then that's not regarded as an official bug.
This is not really. This doesn't bug.
No, of course, we have a lot of things which are not really bugs, so it's features. But they put still in the bug report.
There's a feature report.
Yes, okay, good. So then with that, I think we are done for the summer. Okay, look at this.
Another couple of things I think would be nice, Axel.
What?
And